Hello everyone. In this video, we will discuss Chapter 17, One-Factor ANOVAs for Analysis of Variance. Here's a chapter overview. We will be going over the purpose of the ANOVA test, the difference between t-test and ANOVA, the assumptions and hypotheses of the ANOVA test, how to do the calculations, the difference between among, between, and within, the interpretation of ANOVA tables, post-hoc tests and conclusions, and finally, worked examples. So first of all, what is the one-way ANOVA? It's a statistical test for comparing the means of different populations. While it can be used for just two populations, it's generally used for three or more. It compares the means of these populations by comparing two variances regarding the data set as a whole. It isn't comparing the individual variances of each group per se. If these two variances regarding the whole data set are equal, this means that the means are equal. So we compare these variances in order to compare the means. A one variable or one factor or one-way ANOVA simply means that a single effector or variable with multiple levels is being used in that analysis. For example, one variable could be temperature and it has different levels at 10, 20, and 30 degrees Celsius. So why don't we just run a bunch of t-tests with all of our different pairs in the data set? The reason for this is it increases the chance of committing a type 1 error. If alpha equals 0.05 and you sample a population 20 times, we can calculate how many times we will reject the null hypothesis just based on random chance alone, just by multiplying 20 by 0.05. So 1 out of 20 times we will be rejecting the null hypothesis incorrectly and committing a type 1 error just based on random chance. So we don't want to increase that chance of type 1 error. The t-test, as we talked about before, is the comparison of the means of two samples. The f-test that's used to determine whether we use a Student's or Welch's t-test does require normally distributed data, and that test can be one or two-tailed, though we, in this class, forced it to be one-tailed. An ANOVA, on the other hand, which compares the means of three or more samples, uses an f-test as well, but it's very robust, and this f-test is always one-tailed. There are four assumptions for the one-way ANOVA test. The first is that all of the samples are random and representative. The second is that each observation is independent from the next. Third, each population being compared is normally distributed. And fourth, the variances within each group are equal. Remember from the last chapter, the Fmax test, Levine's test, and Bartlett's test, which allow us to compare variances. Of these four assumptions, the first two are the most important. However, in this class, we will also be testing the variances in point number 4. We will not be testing the normal distribution for the populations in this class. There are two sets of hypotheses for the one-way ANOVA. First, we have the conceptual or biological hypotheses. These relate to the actual question being asked about the data. The null hypothesis is that the means of each group, whether there are 3, 4, or 50, are all equal. The alternative hypothesis is that not all the means are equal, or at least one differs from the rest. The statistical hypotheses relate to what is actually going on in the calculations in the ANOVA. The null hypothesis is that the variance among the groups is less than or equal to the variance within the groups. The alternative hypothesis is the variance among the groups is greater than the variance within the groups. And I hope to clear that up just a little bit with this next slide. But I'll mention here, when we reject the statistical null hypothesis, this also means we reject the biological null hypothesis. In the same way, when we accept the statistical null, we accept the biological null. So the way I've broken this down to explain the one-way ANOVA math is a bit reverse than what you see in the lab manual. So here I start with the end goal of the ANOVA. The final statistic calculated by the ANOVA is an F-calc value. And this is calculated by dividing the mean squares among the groups, which is the overall variance among the groups of the whole data set. That's divided by the mean of squares within the groups, which is the variance within the groups overall as a whole data set. We compare that F-calc value to an F-crit value and find a p-value to come to our conclusions. This mean squares value, MS, is the calculated variance of that data set, and it's calculated by dividing the sum of squares by the degrees of freedom. The sum of squares estimate variability, and we have two formulas here. We have the sum of squares for among the groups and the sum of squares for within the groups. The within groups is considered the error or noise, and the among groups is considered the signal. These formulas are useful for calculating the ANOVA by hand, but we will not be using them in lab because we have Excel and R to do these calculations for us. So this slide is hopefully useful for understanding the difference between these words among or between and within. So that if we have three populations, each of these groups has some variability within that group. This is considered the noise of the data set. Then between each of the groups, so say comparing 1 to 2, 1 to 3, and 2 to 3, we have variability between or among those groups. And I've listed both of those words here because different programs and different textbooks will say different words, either among or between. So the ANOVA is comparing this signal, this variability between the groups, to the noise or the variability within the groups. The output of the one-way ANOVA table is always the same. It's a table that looks like this, with the source being among or between or within groups. The total, then we have the sum of squares, degrees of freedom, mean squares, the F-calc value, and the p-value. It's always reported in this format, and you don't need to calculate the total with a long formula that's shown in the lab manual. You can just sum the values here. The results for this one-way ANOVA table show that the means are different because the p-value is very small. It's less than 0.05. However, it doesn't tell us which means are different from each other. It just says there is a difference overall. When the F-calc value is greater than F-crit and the p-value is less than alpha, we reject that null hypothesis for the ANOVA and conclude that at least one mean among these different groups differs, but we don't know which one yet. For this, we need to perform post-hoc tests. The post-hoc test tests each possible pairing of the samples while keeping alpha near 0.05 or whatever the desired level of significance is. This is again done to reduce the chance of committing a type 1 error. The first of these post-hoc tests is the pairwise t-test with the Bonferroni correction. This test can be done in Excel or R. The only tricky thing about this is the alpha we use to compare for our conclusions needs to be divided by the number of tests being performed in these Bonferroni corrections. So the alpha is not 0.05 anymore, it's a much smaller value to reduce our chance of type 1 error. The second type of post-hoc test is the Tukey-Kramer HSD test. This test can only be done in R, but it's very easy to do in R, and it's very easy to interpret the results because we use the same alpha of 0.05 rather than dividing it by some number. The conceptual theory behind the Tukey-Kramer test is that it compares the observed difference between a pair of groups to the minimum size of the difference that is needed in order to reject the null hypothesis. So the conclusions from the ANOVA and the post-hoc test. After performing the ANOVA, if the means are significantly different, we want to know how they are different. If there's no significant difference, that is if alpha is greater or if the p is greater than the alpha, we do not need to perform post-hoc test. Depending on the size of the data set, the Bonferroni or the Tukey test may be the best post-hoc test. In this class, either one is acceptable. You do only want to focus on the significant results for the biological conclusion. You may perform 6 pairwise comparisons in the Bonferroni test, but if only one of them is significant, you should only talk about that one significant result. Another useful thing is to plot the data to help you describe that difference, whether it's bigger or smaller, higher or lower. It's important to discuss the direction of these significant differences. This slide is a summary of the guidelines for performing a one-way ANOVA. Step 1 is to test for equal variances among the groups using either the Fmax test, the Bartlett's test, or Levine's test. If necessary, you must transform the data and rerun the variance test until equal variances are obtained. Step 2 is to perform the one-way ANOVA. Again, the data input to the one-way ANOVA must have equal variances. So if the data was transformed in order to achieve equal variance, you must use the transformed data in the one-way ANOVA. Step 3 is to do any post-hoc testing if the null hypothesis of the ANOVA is rejected. This would be with the Bonferroni's corrected t-test or the Tukey-Kramer HSD test. Finally, you make your biological conclusions. Always refer to your ANOVA conclusion, that first p-value, and then to any relevant post-hoc testing. Always include relative direction, either higher or lower, bigger or smaller, of the significant relationships. Finally, we have a breakdown of the steps for the one-way ANOVA, and we'll see these in the worked example in Excel. The first step is to obtain the data and your biological conclusions. These are often given in the question. Step 1 then is to identify both the biological and statistical hypotheses. Step 2 is to visualize the data. We want to know what the relationship is just by looking at it, and then we can do the statistical test. Step 3 is to test for equal variances using either the Fmax test in Excel or Levine's or Bartlett's test in R. Step 4 is to run the ANOVA, and today we'll be looking at how to do that using the data analysis tool pack in Excel and how to do this in R. Step 5 is to draw conclusions from the ANOVA test. Step 6 is to perform the post-hoc test if necessary. And finally, step 7, draw conclusions from the post-hoc test. From here, we're going to go ahead and walk through the worked example in Excel, and then we'll go through that same example in R. So let's take a look at this worked example in the lab manual. It's on page 199 in the one-factor ANOVA chapter. And let's go ahead and look at this data together. This data was collected on the level of serum lipid-bound sialic acid, or LSA, in patients with different forms of breast cancer, plus a control group. And the interest in this is that if LSA levels are different in patients with breast cancer, then it can be used as an indicator of breast cancer. So we want to perform an ANOVA on this data to determine if the level of LSA in the samples from different populations are the same, or if at least one of them differs from the others. In the Excel template, this data is already copied into a table. And the first thing we'll do is just type out the question that's being asked about this data that was given in the problem. So the question being asked is, are the mean levels of LSA in these 4 populations or groups the same, or is one different? And this will just help us guide the rest of the analysis. Next, we will write our biological and statistical hypotheses. Remember, these biological hypotheses relate to the actual question being asked. The statistical hypotheses have to do with the math of the ANOVA analysis. So the biological null hypothesis is that the mean LSA levels are the same in all groups. You could also write this out by writing mu1 equals mu2 equals mu3 equals mu4. Either of those are acceptable. The alternative biological hypothesis is that at least one mean LSA level differs. Then the statistical hypotheses, again having to do more with the math of the ANOVA. The null hypothesis is that the variance among the groups is less than or equal to the variance within the groups. The alternative hypothesis is therefore the variance among the groups is greater than the variance within the groups. This is represented in the lab manual and in the PowerPoint with sigma squared. Step 2, I've left space to visualize the data so we can just get an overview of what's going on with these samples. We're going to make two types of graphs. The first is a box and whisker plot, and the second is a 2D line plot with markers. So we're going to highlight all of the data, including the group names. We'll go to Insert, and in the chart section, we're going to click on this little histogram, and the second section has the box and whisker chart. Clicking on that, I'm going to drag it over here so we can edit it, because right now this doesn't really tell us a lot, because the first thing we notice is we don't know which color represents which group. So the very first thing we want to do is add a legend to this graph. Now we can see that the control is blue, benign, primary, and recurrent. We have all of their relationships and colors here. The next thing we want to do, so we know what we're looking at here, is we would like to label the y-axis. To do this, we'll add a chart element, axis title, and primary vertical. And this data is representing the LSA levels of these patients. So I will label this LSA levels. You could also add a chart title. I'm not going to for now, and we don't need a horizontal title. Now we can see, just based on looking at this without doing any stats, that it looks like the recurrent and the primary groups have the highest LSA levels and the control has the lowest LSA levels. Let's make one more chart type. This will be a 2D line plot with markers. So again, I'll highlight all of the data, including the group names. Go to Insert, and this time we'll click on the line chart, and I'm going to click on the 2D line with markers chart. This chart already shows us the legend for the different colors. We do want to add an axis title to the vertical axis again, showing that these are the LSA levels. This will help with the interpretation at the end of the analysis. The next step is to test for equal variances. The way we did this in Excel was using the Fmax test. So the null hypothesis of the Fmax test is that there are equal variances among all 4 of these groups. The alternative is that the variances are unequal. And what we're going to do first is find the Fmax calc value. And remember, this is equal to the maximum variance of the groups divided by the minimum variance of the groups. So scrolling back up, I'm going to go ahead and add another row to this original data called variance. And I'm going to calculate the variance using var.s for each of these 4 groups right beneath it. And I'm going to drag and drop this formula to each cell. And I just want to highlight that in this cell, even though it highlights these empty cells, that's still okay. If you really want to, you can just select the 7 data points there. So for the Fmax calc value, we want to do the maximum of these 4 values divided by the minimum of those 4 values. And we get a value of 2.48. To find the critical value, we need the number of groups or treatments and the degrees of freedom. The degrees of freedom comes from the smallest group. So first we have 4 groups or treatments. So K is 4, And this is just to help organize our thoughts. And the degrees of freedom, we have the primary and recurrent group have the smallest number of samples, which is 7. So the degrees of freedom is 6 for this problem. When we pull up the statistical table for the F max values, this is on page 280 of your lab manual, we have 4 treatments, 6 degrees of freedom, so our critical value is 10.4. When we compare our calculated value to our critical value, we see that the calculated value is smaller than the critical value, so this means that we accept our null hypothesis. And we have equal variances for these groups. This means we can proceed with the one-way ANOVA with the data as is. Again, if we had rejected the null and had unequal variances, we would need to transform the data before performing the one-way ANOVA. To perform the one-way ANOVA in Excel, we're going to use the Data Analysis Toolpack. If you haven't already installed this to Excel, click on the link in the PDF that I'll post to find instructions on how to do that. Once it is installed, it should be under the Data tab on the far right. Click on Data Analysis. And several options will come up. We're going to go to the very first one, which is ANOVA single factor. So that's single factor or one factor, one-way ANOVA. We get an option box here, and it asks for the input range. We're going to select all of the data, including the labels, and then we need to tell Excel that the labels are in the first row. We'll keep alpha at 0.05 unless instructed otherwise. And then we want to change the output to stay in this same worksheet. So we click Output Range, and then we need to select the cell where the data will appear. So I'm going to select the very first cell under this section 4, and then click OK. And after a moment, all of the results will pop up. So we've performed a single factor ANOVA. The first table is a summary of the groups. So we have the N value, the sum of that group, the average, and the variances. Then we have our ANOVA table. So this is where we really want to focus. We have our sources of variance between and within groups, our sum of squares, degrees of freedom, mean squares, F-calc, and p-value. We also have F-crit. This is for the ANOVA. These F values are different than the F-max test values here. What we want to really focus on in this table is the p-value. This p-value is less than 0.05, which indicates that we need to reject the null hypothesis. So let's go ahead and draw conclusions just based on the one factor ANOVA. We haven't done any post-hoc testing yet. So first of all, we reject the null hypothesis because our p is less than alpha. The statistical conclusion of this, let's go ahead and scroll up and look at these again. If we reject the null hypothesis, this means that the variance among the groups is greater than the variance within the groups. Let's go ahead and type that in here. This also means we reject our biological hypothesis. Our biological null hypothesis was that the mean LSA levels are the same, so we conclude that at least one mean LSA level differs. Before we move on to the post-hoc test, I just want to point out that there's another table in this template that shows how to do these calculations in Excel without Data Analysis Toolpack. I'm not going to go through all of them here because we have the Toolpack at our disposal and we are going to use it in the lab section of this class. But it's there if you'd like to go through and see these calculations. So moving on, since we rejected the null hypothesis for the ANOVA, we need to perform post-hoc testing. In Excel, you can only do the Bonferroni corrected t-test. The Tukey Kramer HSD can only be performed in R. So first we need to determine how many tests are we doing. I have listed them here, and all I did was, say, control versus benign, control versus primary, control versus recurrent, etc. There are a total of 6 pairwise tests to be performed. This means we need to divide alpha of 0.05 by 6. So our new alpha for these post-hoc tests is 0.0083. All of the p-values here we will compare to this new alpha to determine if they are significant. To perform the Bonferroni corrected t-test in Excel, we are going to use the t.test function. And we need to enter both arrays or groups. So this is control or normal versus benign. So I put a comma there and then select the second group. I'm going to scroll down so we can see this here. The next thing it wants is the number of tails. We're going to be using a 2-tailed distribution for these t-tests. And then it wants the type, paired, equal variance, or unequal variance. We determined that these had equal variances, so we will also type a 2 for the 4th argument. Running that, we get a value that seems small at 0.01, which is smaller than 0.05, but it is not smaller than 0.008, so this is not a significant result. We'll now do the normal or control versus the primary. So selecting the control, comma, selecting the primary, comma, 2 for 2-tailed and 2 for equal variance. And we now have 0.00025. This is smaller than 0.008, so this is significant. Next, we'll do normal versus recurrent. And you can see this kind of takes a little bit of time as we have to select these and type them in, and there's no easy way to drag and drop this formula. This one is also smaller than 0.008, so this is also significant. Next is benign versus primary. And I'm still using 2-tailed and equal variances, so 2s for those last 2 arguments. This is smaller than 0.05, but it is not smaller than 0.008, so it is not significant. And now we have benign versus recurrent. And again, this is not significant. It's not less than 0.008. Finally, we have primary versus recurrent. And this one is also not significant. So we have 2 significant results from this post-hoc test. For our final biological conclusions, what I'm going to do is I'm going to copy this graph down here, and you can use either one that's more useful for you. But I'm going to use this to help guide my discussion of the results. I'm going to start off just by saying what are the results of the ANOVA by itself. And we found that the LSA levels were different from the ANOVA analysis. That was from our first p-value in the ANOVA table that told us to reject the null hypothesis of the ANOVA. Next, from the post-hoc test, we found that the LSA levels in the primary group were different from the normal group. But I'm going to look at the graph to see how they were different. So again, I'm only looking at the significant results and talking about those in my conclusion. The primary group here is gray, and the normal or control is blue, and the primary group has higher LSA levels than the control group. So in our conclusion, we can say we found that the LSA levels in the primary breast cancer group were significantly higher than in the control group. We also found that the LSA levels, now looking at the recurrent group versus the normal control group, the recurrent here is in yellow and control is in blue, and we see the same thing. The recurrent is greater than the control. So we found that the LSA levels in the recurrent breast cancer group were significantly higher than in the control group. Since there were no other significant differences using the post-hoc test, we can end there. I do want to show you that in the second tab of this template, all 4 of the practice problems from the lab manual are listed here already, so you don't have to spend time typing those out. But what we're going to do next in this video is do the same worked example, but in R. So before we go into R, let's go ahead and make our CSV file that we will import to R for this problem. So the first thing I'm going to do is I'm going to copy all of the data, including the group names, into a new document. The way we're going to set up this document is similar to how we set up the document for the Levine's and Bartlett's test in the last video. What this means is we need to have 2 columns, one with the group name and one with the values. So I'll start with the control. I'm going to cut and paste these values here, and then I'm going to copy and paste the group name next to all of those values. I'm going to go ahead and add a column name here. This will be the group, and I'll call this LSA for LSA value. I'll do the same thing for benign, cutting and pasting these values and copying and pasting the benign group name. Repeating for primary, and finally for recurrent. Next, I'm going to select all of these columns before my actual data and delete them. You can either right-click on the column name and press delete, or come up here and click delete. I'm going to save this file to my desktop. And I'll call this worked example. Remember, we always need to save the file as a CSV, comma delimited or comma separated values. And now we're ready to import this data into R. So I'll open RStudio, make a new script, because we always want to type our commands into a script and not the console, because we'd like to save our data so we can review it later. And the first thing we're going to do is load the data in, but we need to set our working directory to wherever we saved that file to. I saved mine to the desktop, so I'm going to go ahead and open the desktop folder. When we import this data, we want to give it a descriptive name. I'm going to go ahead and call this cancer data, because this was measuring the LSA levels in different cancer groups. We use the read.csv command. I called mine worked example, and I pressed tab to autofill the rest of that name. We do have column names, so we need to use header equals true. Run that line by either pressing run up here with your mouse or Control Enter on your keyboard. Let's take a look at that data using head and the object name cancer data for mine. And we see that we have 2 columns, the group column and the LSA column. One more command I'm going to run here is called length. And this will be the length of the cancer data object. And we have 2 columns. I want to know the length of each column, so I'm going to run the command length on cancer data column LSA. And we see that there are 34 input values for the LSA column. The reason I do this is just to make sure all of the data was input for this problem in R. And you can check this by selecting just the data points in Excel. And looking down here, we see count 34. This means there are 34 non-blank cells in this data set. and that matches what I found in R, so I know that all of the data was successfully imported to R. The next thing we'll do is actually look at the data. To do this, we'll use plot, and this command will be a little bit different. It's going to be LSA, that's the column name, and then the squiggly dash, which for most of you will be at the top left of your keyboard, and then group, so this is the LSA data according to the grouped data in the data of cancer data. This is just the syntax for the plot function for this type of plot we're going to look at. When we run this command, we immediately get a nice box and whisker plot. The only thing that's different from this plot than the one we made in Excel is the order. R by default will organize the x-axis alphabetically. So it is possible to organize this on your own using numbers in front of the words. I'm not going to do that here because it's a little bit out of the scope of this class, and it's not quite important because we can still compare benign to control and primary to control and do all the pairwise comparisons we'd like to with this data. But we do see the same trend where the primary and recurrent groups seem to have the highest LSA levels while control has the lowest LSA levels. The next thing we're going to do is to make sure that this data has equal variances. I'm going to use the Levine test, but to do that, I need to load the library car. So I'm actually going to scoot down this data here and load in library car at the very top of my script. And remember, this is something that we used install.packages with last week if you haven't already done so. So if you did not install the car packages, when you run library car, you will get an error. So make sure you review the chapter 16 video on how to do that. So we're going to use Levine with a capital T test on the cancer data, the LSA column, and I'll use the squiggly line here again. This is a little bit different than what we did last week, but it works just the same. So either method is fine, but I want to be consistent with the ANOVA test syntax. So here we'll do the Levine test on the LSA column from the cancer data according to the group information from that same data set. And we take a look at the p-value here, it's 0.5853, which is greater than 0.05, which means we accept our null hypothesis. And we have equal variances. So we can continue with this data straight to the ANOVA rather than performing any types of transformations. So now we will actually run the ANOVA analysis. The function for the ANOVA is AOV, and the syntax, the inside the parentheses, is the same as what I did in this Levine test. It is the data values according to the data groupings. So I'm going to go ahead and just copy this text and paste it into the AOV function, making sure it's in between the two parentheses. And when we run that command, we get something that looks a little bit different than what we might have expected from what we saw in Excel, because all we have here is the sum of squares and the degrees of freedom of the groups. And we also have residuals. This function by itself, we're actually going to save it to a new variable. There's actually two ways to do this. So the first way I'll show you is to save it to a variable, and we'll call it results. And when we run this line, there's no output because we saved everything that was put here into the variable named results. Then we're going to do another function called summary on the results object. Running that will output a table that does match the one we saw in Excel. Now we have the degrees of freedom for the within groups and among groups, the sum of squares, the mean squares, the F-calc value, and the p-value. Again, focusing most on the p-value so we can determine if we need to do post-hoc testing. Here, the p-value is less than alpha, so we reject the null hypothesis for the ANOVA. This means we need to do post-hoc test. The other way to run this ANOVA in one line is simply to do summary of AOV, the ANOVA of cancer data, column LSA, according to cancer data, column group. So we are nesting the function AOV for ANOVA within the summary function, and we get the same output as we did in the previous line. So you can either do lines 11 and 12 or just line 14 and get the same results. The next thing we'll do is the Bonferroni corrected t-test. And remember, for the Bonferroni test, we do have to divide alpha by the number of tests. So again, I would recommend looking at the plot and determining how many tests you have. Here we have 6, so we can just do 0.05 divided by 6 in a line in R, and it will give us our new alpha to compare our p-values to. To run the Bonferroni tests in R, we use the command pairwise.t.test, cancer data LSA, cancer data group. So we have the values in the first argument, the group information in the second argument. Then we need to set 2 additional arguments. The first is p.adj for adjust equals, and in quotations we need BONF for Bonferroni. We also need to set the argument pool.sd to true. And you don't need to know why we set these to what they are, but you do need to know that you have to set them to this if you're going to use the Bonferroni test in R. Running that line, this gives us a nice little table comparing control to benign, primary to benign, recurrent to benign, and etc. And you see that there's dashes in this upper triangle of the table because they are the same comparisons as seen in the lower half of the table. And again, we are comparing these p-values to this new alpha of 0.008. We do find the same results. The only significant values here are primary versus control and recurrent versus control. And we found that in Excel as well. And we found that the primary and recurrent were both significantly greater than the control. The last thing we'll do here in R is the Tukey-Kramer HSD test. This function is Tukey HSD. And instead of entering the actual values and groups, we're going to enter the results of the ANOVA. So if you did the ANOVA in an object called results, I'm going to copy that and paste it here. Before I run that, I'm going to show you, you can also do the Tukey HSD command on the entire AOV cancer data according to cancer data group. Copy that in, and I'm including the first parentheses on that inside the parentheses of the Tukey HSD command. So now we're nesting the ANOVA within the Tukey HSD. Running either one of these lines will give us a little bit of a different output. So instead of a table, we have just rows of the p-values. These p-values we are comparing to 0.05. We did not have to compare it to a smaller p-value. The Tukey HSD takes care of that type 1 bias by itself. So here we have the control versus benign is significant, as is the recurrent and benign. We also have, oh, I'm sorry, that's actually greater than, so not that one. The control benign, the primary control, and the recurrent control. So this one actually gave us a slightly different output, with the control and benign group being significantly different, and that's okay. Both of these tests are perfectly acceptable for postdoc testing of one-way ANOVAs, and both will be accepted on any lab exam for this class. So from this, let's draw some conclusions. So first, we just said we rejected the null from the ANOVA from the postdoc Tukey test. We also find that the control versus benign, control versus primary, and control versus recurrent are significantly different. For an exam or for any type of analysis in like a paper or journal, you would want to go into more detail about which one is greater or less than the other ones. But since we already did that in Excel, I'm not going to type that again here. Last thing we'll do, as always, is save this script. This is chapter 17, one-way ANOVA. And with that, we conclude our video on chapter 17.